Okay, so we have a little summary / overview of the Hubble tension, both from the experimental and theoretical side. So it will be mostly like a minor review. So let's start basically with what we know already. So we know that the CMB that we see in the sky, the cosmic microwave background, is almost a perfect Blackbody. This is the well-known result from, for example, FIRES, that it measured the spectrum of the Blackbody. And we know that even if we enhance the error bars by 500 sigma, it still looks like an almost perfect fit. This is because there's a huge agreement of with the perfect Blackbody. But of course, it's not a perfect Blackbody, or it is an almost perfect Blackbody, but not with the same temperature all over the sky. So there are different sky locations, there are different temperatures. Of course, one from just our dipolar motion, two from some foregrounds from galaxy and so on. But if you remove all of these, you get left with these CMB and isotropies, which are basically what we can observe in the sky, that in different directions you still have a Blackbody spectrum, but with different temperatures. So red means slightly higher, blue means slightly lower. So here I've done like a little mock image of how such a CMB measurement could look like. You notice that it's not the default shape that it's usually presented as. I chose to put it in like Cartesian coordinates because this will make it a little bit easier to zoom in. So we can zoom in basically into the middle of this patch here. And there we see this like small bumps. And we can look at kind of the different correlations between these bumps. We see that when there's a warm spot, it's very likely that there will also be a cold spot nearby. So there's some kind of correlation. And now I can draw these kind of rings around like dense centers, hotspots. And you can see that always around these hotspots, there's also like usually like a big collection of cold spots. Of course, it's not always because there's some statistical fluctuation here, but generally there's more cold spots in a range of about this radius from a hotspot. Actually, it turns out that from this you can already measure some CMB correlation functions, which is quite fun. So if you take, for example, these circles and you measure what is their angular separation, it's about 0.8 degrees. And we can do that, of course, for all different angular separations. And what we get is a well-known angular power spectrum of the CMB, where you can see that there's a top axis in which I've written down the angular scale of the multipole. And you see this very prominent feature at around 0.8 degrees, which is exactly a multipole of 220 or so, which corresponds to these kind of very strong correlations that I talked about. Of course, you also have weaker correlations on different scales. So for example, on twice or 3 times that scale. And these are, of course, as you might know, predicted by the Lambda-CDM model and also by the acoustic oscillations in the early universe. Okay, so here I'm showing in orange dots with blue error bars the Planck 2018 measurement of this angular correlation function as from the maps that we saw before, basically. And in green, I'm showing the best fitting Lambda-CDM prediction with little gray bars, which correspond to the so-called cosmic variance, which is like a theoretical uncertainty from simply observing one universe, even though the underlying theory that describes this is, of course, stochastic fluctuations. So like the primordial quantum fluctuations, as you know, generated these CMB anisotropies. So then the question is, what kind of scales can we see in the CMB picture? So there's, for example, the angular scale of the first peak that I talked about to you before. And this was what we immediately saw on the map. But there's also some other interesting features. So for example, there's a strong damping of the higher order peaks here, which is given by this damping tail. There's a lot of other things, other different effects, and they all correspond to some kind of a physical background effect. So for example, there's the height of the first peak. There's the Sachs-Wolf plateau tilt, the odd ratio of the peaks, and an overall amplitude and tilt. Now, all of these also relate to some cosmological parameters. So, for example, the overall amplitude and tilt, they're guided by the primordial power spectrum. Because if you have a primordial power spectrum, which is just overall higher, also your overall CMB will overall be higher. If you have like a more tilted spectrum, also your CMB will be more tilted. And there's a lot of these different cosmological parameters that you have here. So for example, theta S is the so-called sound scale, angular scale of the sound horizon. And tau rho is the reionization optical depth, which basically, since we have a lot of scattering of the photons at reionization, we have like a suppression of the power of the CMB because they're not part of this nice spectrum anymore, but they get rescattered almost randomly. So this means that we have some suppression at L bigger than around 20 or so, which means that it's partially degenerate, for example, with AS. So you can extract a lot of nice information about all of these different cosmological parameters from this image. And this is basically what Planck does. And these are the parameters left. Let's order them quickly to the left. And let's think about what they kind of give you. Well, these parameters below, they give you some primordial information and some information about reionization. While the parameters on top, they give you really like more information about really the cosmological contents of the universe. So this is in particular matter, baryons, photons, and neutrinos that are kind of the standard ingredients. So in particular, this would be cold dark matter, baryons, neutrinos, photons. And we, of course, have the Hubble constant in there somewhere. So to talk about the Hubble tension, this is why I'm leading up all of this, is we want to kind of extract from the CMB the Hubble information. And usually people just say, okay, you have the sound horizon, and then you somehow get the Hubble constant out of it. But that's, of course, not as trivial as many people believe. The sound horizon, if you write it down, the expression, it's just the sound scale divided by the angular diameter distance to the CMB, meaning that you have this very complicated expression of the sound horizon in here, which actually depends on a lot of assumptions. It depends basically on the expansion history all the way before recombination. So this depends a lot on what kind of dark radiation do you have, how hot are the photons, and we also have some dependency on the redshift of recombination itself, which depends on how homogeneous was recombination, for example. And we have this dependence on the angular diameter distance, which basically sums up the information from all below the given redshift. This means that there's quite a lot of redshift range from 1000 to 0, basically, that we're also somehow mangling in this. And only in the assumption of the basic lambda CDM model do we have like a almost immediate way of getting some information from this. Turns out that this is basically in lambda CDM, with a fixed CMB temperature and a fixed number of neutrinos. This is basically the product of this omega m h cubed factor and this omega b h squared factor, each to some power. And now the question is, how can you disentangle this information? In particular, you want to get at this Hubble parameter, but it's not immediately obvious how to do this. So for this, we can look at other things. So for example, this R ratio here, which comes from the amplitude of the even versus odd peaks in the CMB. There you can get some information about the baryons because the amplitude of the even versus odd peaks is guided by the offset of the CMB acoustic oscillations. And these have a term proportional to R in them. It's some potential times 1 plus R. Okay, so this ratio of even to odd peaks, it actually gives you almost a measurement of the ratio of baryons to photons, which guides this strength of the fluctuations. And this gives you indirectly a measurement of the baryon abundance if you assume some fixed photon temperature. Okay, with this you can basically eliminate the second factor here, and you're left only with omega m h cubed. You still have a very precise measurement, so this is very surprising. So on this combination, you have about an accuracy of 0.05%. On after marginalizing with this knowledge, you have on omega m h cubed still a measurement of around 0.3 or 0.4%. So this is still extremely precise, meaning that if we had a very precise measurement of omega m or of omega m h squared, we could immediately get our Hubble value with a high precision. Sadly, the precision with which you can get omega m h squared or omega m is not as high because we can look at what various terms it appears in. We have here the damping envelope, which that is a very much function that depends on very many of these parameters. So it's not quite trivial to extract some immediate information on omega and h squared on this. We have the the redshift of equality, which has like multiple effects on the CMB at the same time. But from this, you could in principle get a very precise information on omega and h squared, except that the dependence is not strong enough to really get like a sub% level measurement of this. Similarly for the omega lambda, which does this kind of ISW plateau suppression, but the ISW is very large scale, so you don't have a lot of modes, so you don't have a lot of precision of measuring this. So again, you don't have super high precision, meaning that you combine your very high precision measurement of omega m h cubed with some lower precision measurement of either omega m or omega m h squared from the CMB, and you get some decently accurate measurement of the CMB. Okay, in principle, I should mention that there's of course also CMB lensing and different effect of these parameters on polarization, of course, which you can also extract information from. So assuming then some certain cosmology, we can use these degeneracy directions, and we can get a measurement of H0 from the CMB, also of the other parameters like omega m. So we've basically decorrelated the space under the assumption of a given model, and we get our usual contours, 68.3 and 95.4%. But we can also zoom out of these contours. Oh, I don't do that yet. We could also zoom out and show that there's another measurement which comes from the distance ladder. So let's quickly talk about the distance ladder, because I think it's much important to also know the other side of the story, not just one side of the story. So here I'm showing you the distance ladder basically. So I've plotted here the distance of some objects like the Milky Way object, starting with Black Cloud, M31, and NGC 4258. And these are some objects where we know the distance. So Milky Way, it's pretty easy. You know some parallaxes, so using Gaia or whatever. Large Magellanic Cloud, basically the same story. For NGC 4258, since it's so distant, you have to be a bit more creative. So there's some water masers in this thing which circle around a black hole, and from the acceleration and velocity, you can kind of measure the distance of this object, which is a very nice thing. And you know it's redshift, so then you get the information about here, the luminosity distance that you want. Okay, but this is kind of the x-axis. On the y-axis, we have something different. On the y-axis, I'm showing you the observed magnitude minus some arbitrary normalization, some big M. This normalization, I'm playing around with it. I'm trying to see what can it be. So if I take a random normalization, I will not get like the perfect line up. This is kind of the line where n minus n equals this 5 log d, etc. I will get some random lines, and only then by changing what my m is, I can kind of try to bring them into agreement. So this will give me then this kind of big M that the Schuh's collaboration uses. If I use a different one, I will not have this perfect agreement. Now, why should they agree this big small m minus big M? Why should it be 5 log of the luminosity distance? Well, this is related to the definition of this magnitude. So this magnitude is kind of related to how bright is something, which corresponds to how luminous the flux is that we observe. And this you can almost directly relate to the luminosity distance of the object, of course. And then you get this kind of way of relating that the magnitude has to be some function of the luminosity distance. This is kind of how it works. Okay, so only if you choose this big M correctly do you get kind of the straight line. So you can kind of measure from the x position of these objects. You know that you have to adjust the height such that you get perfect agreement, meaning that you can calibrate. What is this? Well, it's the absolute magnitude of the Cepheids in your Schuh's sample. Okay, so this can be used to kind of calibrate this absolute magnitude of the Cepheids. So that's our first step of the distance ladder. We just calibrate the Cepheids. Now, the Cepheids we can now use to calibrate the supernova. How does it work? Well, we know what their observed luminosity in some more distant objects is. We know what the absolute luminosity is because we just calibrated it. And now we do the same game with the supernovae. We have some supernovae observed luminosity. We can change the absolute magnitude of the supernovae as we want. So we can scale it up and down, and until we get the correct agreement, and then we stop and we find what is the absolute luminosity of the supernovae. Last step. Now this one is interesting because this is not anymore about calibration. This is about inference. So the third step of the distance ladder that we have here is about inferring cosmology from the distance ladder. So M is again the absolute luminosity of the supernovae. We know what is M minus M because we measure it. And now we want to plot here 5 times the log of the luminosity distance plus 25. So we simply use the same law as we did here, except now that we use it for the supernovae. And we know that if the luminosity distance was higher, it would not agree with this kind of flux anymore. So if we have a given flux, we know that we have a given luminosity distance. Okay, so this means we can infer the luminosity distance. So all of this is to say that, okay, we have now found luminosity distance of objects which are not only 25 magnitudes away, like they are instead 35 or 40 magnitudes away. That's the whole point of the distance ladder. If we could observe them directly, the luminosity distances, we could just use that directly. But sadly, we cannot. So we have to be creative and do this whole internal calibration. Now, what is this used for? Okay, we have seen we can calibrate the Cepheid absolute luminosity. We can, from this, calibrate the supernovae. This is usually in the B band, which is why it's called B. And then we get our luminosity distances. We also know the redshift of these objects because we've measured it for the supernovae. And this actually gives us then the inference of H0. And it's very simple kind of geometric kind of measurement because you know a bunch of luminosity distances which are inversely proportional to H0. And then you know what your H0 has to be such that with the correct redshift you get out the correct luminosity distance. That is kind of the distance ladder. And the result that it gives us is very different from what we saw before. This was the Planck measurement that we had before, assuming the LCDM. And this is now the new measurement that we get. Now, this new measurement, of course, also has a bunch of assumptions and systematics in it, which are related, of course, to, for example, the supernovae, the dust extinction of these, and how bright they are, because we're always talking about these observed magnitudes. And if these are not measured like as the intrinsic observed magnitude, so to say, if they are somehow obscured by dust, you will measure kind of the wrong magnitudes. And the same is true also for all the intermediate steps, especially with the Cepheids, where there's recently some discussion that maybe there's a break in the absolute magnitude of the Cepheids because they're not perfectly standardized. And then you get into like the whole problematic feature from the other side. So both sides have a lot to work on, basically. And this is also possibly the reason why in the lambda CDM model, we get a huge discrepancy between the parameters that one data set prefers and the region of another data set that another data set prefers. So this is within the model, the two data prefer different regions. Of course, this could be simply because we have the wrong model and we are analyzing under the wrong assumption, or it could be because either data has some systematic and it should truthfully be here or this should be there. So the tension currently is around 4.4 sigma, at least between Shoes 2020 and Planck 2018, which gives you like a 1 in 100,000 chance that this actually happened randomly in the lambda CDM cosmology. Okay, so it's not very likely. So that's basically Hubble tension, but only part of it. So what I've talked about to you before is basically the bottom part here, the Planck CB anisotropies. We also have the top part here, which is the Cepheid calibration of the distance ladder. And you can see here that there's quite a disparity. But this, if this was the whole image, you would just say, okay, there's some systematics here, let's move on with the discussion. Sadly, that's not the whole image because we actually have alternative measurements of both sides, so both of the data here in the universe. So here we have some selection of non-Planck CB anisotropies, and I've purposely chosen the ones that have the highest and lowest H0 values. So this is why, for example, you see the SPP Poil measurement in here, which is not often cited, but it's one where the H0 value is actually relatively high compared to all the other measurements. Yeah, and you can see here some examples of how these are measuring the CB anisotropy tail. Okay, then there's my next one, which is going to be about Bao and BNB. It's like my favorite. That's why I do like a little excursion on this topic. So we need to go beyond the CMB to probe this tension independently. And one such example is combining Bao and BNB. So BAO, as you might know, it determines the matter fraction and this product of H0, so the Hubble parameter, and the sound horizon. Why is this? Well, what BAO measures basically is like the clustering of galaxies in some kind of radial sphere around some central galaxy up to redshift space distortion effect, which I'm going to ignore for the moment here. And this gives us some redshift distance for these galaxies where they're more clustered and some angular distance where they're more clustered. Why are they more clustered? Well, because there are some acoustic oscillations, and these are imprinted in the power spectrum, and they are related to the sound horizon. So on the scale of the sound horizon, you have some more clustering. Though I should be more careful here, slightly bit more careful here. It's not actually the sound horizon which goes here, but it's actually the drag horizon, which is at slightly lower redshift. And thus, if you have a very fancy cosmology, you could actually start to disentangle the BAO from the CMB sound horizon. So you would have the drag horizon for the BAO and the sound horizon for the CMB. Now, there are some papers which are kind of studying like how does this relate, the drag horizon and the sound horizon, and they usually find that like most cosmologies is a very tight relation between them, and so you can use both of them interchangeably. But of course, that's not always going to be given. So this is a slight assumption that you might want to care about in fancy cosmologies, which have like a change around or right after recombination. Okay, so you have basically the measurement of the redshift distance and some small redshift distance and some small angular distance, and these relate respectively to the two formulas that I've written down there. And the important thing is that we immediately see here this measurement of H0 times Rs in all of these, but there's also this kind of H of Z over H function, which this is what's related to omega n basically. So I'm doing here some expansion at high redshift, so that I can basically ignore the dark energy for now. But of course, or rather, let me reformulate. I'm not doing a high redshift expansion. I'm doing a reformulation of the omega dark energy in terms of 1 minus omega n with a cosmological constant. This is what I should have said. Okay, sorry. And here is some possible radiation term. Okay, and this means that for BAO, where the radiation is basically negligible because it goes with 1 plus redshift to the 4, this means that we basically almost have a measurement directly of omega n, assuming standard dark energy, of course. Okay, so this is how it looks like. You take your BAO, you take, for example, galaxies, you measure the BAO in them, and then you get these contours in here, Hubble parameter, Hubble times Rs, omega n. So that's the 3 parameters that I'm going to look at now. And you can already see that, for example, for these galaxies where I measure the BAO, I can't measure H0 from the BAO itself, but I can measure this product of H0 times Rs very precisely here. And similarly, I get some measurement of omega n. This is exactly what I promised before. These two things are measured, at least in some assumed lambda SDM model where I can replace omega dark energy with 1 minus omega n. So H0 remains itself undetermined, but the product of H0 Rs remains well determined, and it gets the more determined, the more different redshifts you include. So if you include different redshifts, as we have seen on the slide before this one, you have basically many probes of H of Z over H at different redshifts. So this means that you more and more determine this omega n, and also you kind of break the degeneracy between the term on top and the term on bottom. If you just have one measurement, it's hard to disentangle these because it's like a fraction of two things. But if you have like 10 measurements of these, you know, like the denominator changes, the numerator stays the same, so you can disentangle them. That's why the more measurement of different redshifts you take, the more well-determined your contour becomes. And the green combined contour of line alpha in galaxies gets very, very small. Now, let's look at the two things. So omega m might be used as a cosmological parameter, but we want H0, not H0 times Rs. So we can look at the product of H0 Rs, and we just write it out. What is it? Well, it's once again this function of H of Z over H0, and it's a sound speed integrated over redshift. So we know what the temperature of the CMB is, at least in from the measurement of the virus. We know also, because of this, what is the physical amount of dark radiation, physical amount of radiation, because we assume no dark radiation, we just assume standard neutrinos, and thus we get kind of this very nice correspondence. We have measured from the BAO themselves, this omega n parameter, So there's just two parameters left here that we kind of have to determine to make this measurement. And the first of them is omega b times h squared. So this is where BBN comes in. If you somehow had some external information about this from BAO, you could measure just from BAO the H naught, which is kind of why, for example, the shape fit might be interesting if we somehow get information on the baryon fraction, meaning that if you get this from shape fit, we have H naught directly from BAO basically, which would be very nice, of course. So how does BBN do it? Well, BBN measures basically abundance of helium and of deuterium. And here you can see I plot the helium abundance in this kind of colored plot. I plot the deuterium abundance in this gray scale. And you can see the two measurements here. And you can see that for different parameters of the baryon fraction and the number of neutrinos in our universe, you get different predictions for the abundance of both helium and deuterium. You can see, very importantly, this is kind of why I'm showing this, that the abundance of baryons is basically fixed by the measurement of the deuterium, which is currently assumed to be very accurate. And the measurement of the helium is basically just there to constrain the number of extra relativistic degrees of freedom. So that's kind of an important thing to keep in mind. So a small story about why does omega b h squared actually matter for the helium abundance. Well, basically, you have the number of baryons, of course, is proportional to omega b. So this means that the fraction from baryons to photons is, of course, dependent on omega b times h squared, of course. And this basically determines the time where you have this kind of decoupling of the elements from the photons. So this is not recombination, this is not the ionization, but this is the photo disintegration of the elements. But it has basically the same decoupling. So if you have more baryons, you will decouple, of course, at a later time from these photons, meaning that you will have a longer time at which you stay coupled, and then your expansion history at this point will be different. Okay, so the more baryons lead to earlier decoupling, meaning that you have a higher temperature at this. That means you have a more efficient deuterium burning, meaning you have less deuterium and slightly more helium. And so that's kind of the story of why you get this kind of shape of this line here. Okay, but it's not like the most important part. The most important part is that we get some constraint on omega b h squared, which we can then use for our BAO plus BBN. So now I show again BAO only. And now with BBN, we get this omega b h squared, meaning that we will be able to measure H naught. Okay, because we now have a one-to-one relation between H naught RS and H naught. So on the right-hand side, now you can see, this is the difference. So the difference is really, you can see it almost directly in this H naught RS and H naught space on the bottom right. This is where I want you to focus. Basically, what I do here is I simply add BBN, and you can see that I get these kind of very straight lines for each of these probes. This is simply that I have now H naught RS as a function of H naught. I've broken this kind of degeneracy because I have now determined all the ingredients basically that I need to convert one into the other. Okay, this means that for each value of H naught RS that I've measured before, I also get a corresponding value of H naught. And thus I get a measurement of H naught, which in both cases is not particularly well. I want to stress this. This is not like a super good measurement of H naught. Only if you combine all the different redshift information do you actually get a good measurement of H naught RS, and thus also good measurement of H naught. Now, a lot of people will then say, okay, but this is only about H naught. They will say, okay, but you have two completely different, completely compatible measurements of H naught. And thus, if you combine them, you suddenly get a different parameter region. But actually, it's slightly more complicated because what have we done here for the blue contour? We've also combined a lot of bananas from different redshifts to get more precise measurement of H naught RS. So why are we not allowed to do this for the red and the blue contour also to get the green contour? And then once we have the green contour, it's really just this breaking of the degeneracy, which will immediately give you also H naught measurement. So then you would also have to argue about the agreement between the other measurements. The point still somewhat stands because these two things here, blue and red, are the ones that have the biggest difference of all the BAOs. So if you look at all the BAOs, the Lime Alpha versus the Galaxy, that's the biggest kind of separation. So here we have once again the same picture as I said before. Now in H0 omega m parameter space, and I quickly want to say a few things about this. So we can look at where is Planck, where is shoes. So Planck is this contour down here. This is the purple one. Shoes is this band up here. And Planck has about a 0.5 sigma agreement with the green contour, while Shoes has a 3.2 sigma disagreement with this contour. So this would imply that that the tension would be more in favor of Planck. This works, however, is it robust? So we could now imagine, like, what if our model is not just plain lambda CDM, but we have some different model. So it's always nice to test your probe for model dependency. So for duct radiation, it actually turns out that, oops, the contours look almost exactly the same. There's like a little broadening, but this is kind of a little trick that BBN people, of course, like to play. So you still have H0 RS going to H0, so that still works. Because from BBN, you don't just have a measurement of omega BH squared, but also of N effective. So in truth, you're not really adding a lot of dark radiation here, because basically you constrain it also at the same time from BBN. That's also where the second power of BBN comes in. Now, if you do something else, like you shift recombination, could you ask yourself, does it still work? So you could now think about it again, like these formulas and how does it work? Well, in this case, omega B is not what guides anymore how big is the sound horizon, but it's actually the redshift of recombination. If you make it 10 times bigger, your sound horizon is also going to be much different. Okay. This means these are the constraints that you suddenly get. This is a green contour from before. There's no way of knowing anymore. It's completely broken. So you have to be slightly careful with this. So if there's any ingredient not measured by BBN that somehow breaks this tight relation of sound horizon as a function of H0, omega M, and omega B, you immediately lose all your constraining power. Okay. But let's assume that you've done this measurement. You assume it's lambda CDM because the other ones also honestly they also assume it. Then you get some measurement here, which is more in agreement with Planck as before. Okay, let's look about some others. So we have here tip of the red giant branch. There were two recent analyses. It's now like a very nice hot debate between the group led by Wendy Freeman and the group led by Alan Rees. And of course, now we have here like a Hubble, Hertzsprung-Russell diagram of some galaxy, and or in this way the globular cluster. I should be more careful. These are kind of the main sequence stars. You can see the nice different branches, and you can see here this giant branch. So this is where the stars they start to blow up at the end of their life cycle because they've basically burned all of their hydrogen. Now they have to start helium burning, and this is where they get very big. But at some point they will suddenly have fused up all of the helium, and they will get like a very drastic process, like, oh, my helium is gone, now what do I do? And it's this very sudden thing. So this is why you have here the tip of the red giant branch. The stars continue to evolve, continue to burn more and more and more and more, and then suddenly it's all gone, and suck you're down here. So you start to go to this asymptotic horizontal giant branch, and then some stars end up back here, but it's all something different. Okay, but here, what you can measure here is that there's like almost a step in the amount of stars that we have in this Hertzsprung-Russell diagram. So in this case, a step in this luminosity function, and this will be giving you the luminosity, the intrinsic luminosity of a galaxy. So who cares if it's an intrinsic luminosity of a Cepheid, of a supernovae, or of a galaxy? Of course, you can do the same principle, the same game that we've done before, except that you've now calibrated it. For example, within our Milky Way, you've looked at the Hertzsprung-Russell in the Milky Way, you've determined what is M minus M, and you use that for whatever other galaxy that you want. And thus you can get a new measurement of, for example, the supernova calibration. Or if you want, you could also try to use the TRGB directly for Hubble inference, but this has not been done yet because there's not so many TRGBs yet, at least as far as I know. Okay, here's just a zoom in once again, where you can see kind of that if you change, of course, your Hubble parameter, then this object is further or nearer away from the luminosity distance perspective. And then, of course, you would have different kind of absolute luminosities of this object, and thus different kind of points at which there is this step. And you can see that the step seems to be very clearly around like 67 until 72 or so, but it's not really going in the direction of 74 or 76 or anything higher. Okay. There's one more thing, or there's a few more things. So these were kind of the Cepheus and the TRGB, which are the most direct and most well-constrained ones. But we, of course, have a couple of other ones. So this would be based on the Cepheus or the TRGB, but then not using supernovae, but actually using the the Bionic telefischer relation, which relates like the velocity that stars turn around some central galaxy with the mass of the central galaxy, for which you can kind of estimate the velocity. Okay, which also gives you then a measurement of the Hubble parameter in the same way that we've seen before. Other things where you can do it is basically masers. So this is kind of where you have these objects flying around the central black hole. From their velocity acceleration, you can measure the position of the central black hole, the distance, and thus you also get, once again, a measurement of the Hubble parameter. And another one is mirrors and surface brightness fluctuations. What are mirrors? Mirrors are basically an alternative to Cepheus. It's basically the same principle, except that's a different kind of stuff. So there's not much to be said about this. Surface brightness fluctuations, similar, except that it's not a star, but it's like the fluctuations of the brightness of a galaxy, of the surface brightness of the galaxy. Okay, which also has a relatively tight relation. You see it's not super tight, but in any case, you can also make an inference. Okay, you can see that all of these measurements have significantly higher error bars and lie at different positions depending on the precise measurement. And these are kind of like I would call them the secondary local distance ladder measurements, because while they exist, and they're often used to say, okay, there's like an independent confirmation of the local distance ladder, Hubble tension. If you calculate the tension from these, it's like between 2 and 3 sigma. So it's much not as significant as from the other components. Okay, you have strong lensing, and this started with the bottom picture here, with this very clear indication that we should be perfectly in agreement with the Cepheus. So let me first explain what is strong lensing. Basically, you have some background quasar, which has multiple images from some intervening gravitational lens. They converge again onto the observer, and so you have multiple images. And these images, they vary. Why do they vary? Because the quasar in the background has some different fluctuations that you can see, for example, here. And the different images, however, will pick it up at different times. So here we have image A, B, C, D, and you see that there's this characteristic feature. You go down, up, down, but at the different quasars, it will be slightly shifted. And if you just have enough of these features, you can kind of do a statistical analysis of how far are they shifted on average. And then you can get what are these time delays. So here it would be 0.5, 0.4, 0.3. And with these time delays, you have basically an almost direct measurement of the Hubble parameter, because the time delay is actually inversely proportional to the Hubble parameter. Because it's 2 distances over 1. So you have 1 over h0 squared times h0. Okay, so that's basically the whole idea of this. However, as you might imagine, there's like a crazy gravitational lensing system. So this, of course, depends on the modeling of this crazy gravitational lensing system. How much are they delayed or not? And this is actually where this second part here comes in. So this is assuming some stellar dynamics based on the TD Cosmo catalog of stellar dynamics in our local neighborhood, and then applying that and just saying, oh, what if these lenses that we have the same kind of stellar profile as the other things that we've seen before. And you get much higher error bars, of course, because you've now dropped the assumption that this is just a simple NFW profile. And you also shift the mean value depending on what precisely you do. So you can do it in different ways. So for example, if you look at isotropic versus anisotropic profiles, you also get slightly different mean values here, but always the error bar blows up and the measurement is not decisive anymore in terms of this tension. So only under the assumption that you have a NFW profile plus some power law for the stars do you get a very precise measurement, but then it would be pointing more into the reset island. Okay, so the last one is, of course, the gravitational wave standard Siren that we all know and like. It's basically like knowing the distance from the gravitational wave from the precise spectrum of the oscillations, basically. And then by identifying also some electromagnetic counterpart to this that has been seen in neutrinos and gamma rays and so on and so forth, you also get the redshift, because you know what object it originated from, and distance plus redshift it's our old equation. It's always the Hubble constant, of course, assuming some value for omega m and so on and so forth. But you can always combine with supernova if you don't care about omega m. Okay, which gives you some measurement. It's not very precise because, of course, the distance from the gravitational wave is not super precise because it's, for example, correlated with the inclination angle of these objects compared to Earth. And thus you do not get a super precise measurement of the distance, which means that the redshift doesn't get you that much more. So you get some very large error bars on the Hubble constant. So this one is like promising for the future, maybe depending on how many more electromagnetic counterparts we observe. So if we only observe dark sirens, I was recently in like a series of talks, you do get like a 1, 2, 3% measurement of the Hubble constant, assuming a lot of things about the distribution of such objects, but it's not as clear as just getting lots more objects with electromagnetic counterparts. That would be the coup de grace, basically. That would be shrinking down these error bars much more. So possible solutions. There's many data sets that confirm this. So let's talk about the solutions. So you could do this, which is an excellent review by Eleonora Di Valentino. There's just a lot of models, and you basically have a comprehensive summary of all models. These models, they were all tested against different data sets. So you can see there's all different data sets. So it's not quite clear how to compare them apples to apples. Still, let's try to put these models into 3 kind of sets. So we're going to look at late time solutions. We're going to look at early time solutions and dark radiation solutions. So late time solutions, I just call everything that modifies basically far after recombination. And early time, I call everything that modifies around or before recombination. Same with dark radiation solutions, except there I'm going to focus explicitly only on things that are dark radiation. Okay, so how do late time solutions work? Well, the idea is, of course, simply to change the Hubble constant at z equals 0, because then you change h0. Okay, very simple idea. Why is it not going to work very well? Well, because the sound horizon is fixed based by CB, by BAO, and so on, by all these different measurements, meaning that the sound horizon here is kind of a well-determined quantity. And now what you're trying to do, you're changing h of z, which means that you're also changing the angular diameter distance. So this is not varied in late time solutions. So you cannot vary this as well if you don't want to screw up CMB and BAO. So then you suddenly have this problem of how to change h of z while keeping dA of z constant. So basically, this is the formula for the angular diameter distance, where here I've put the explicit expression of h of z. And when you increase h naught, you kind of scale this dA up all the same. But then if you do some, like, let's say you slightly decrease the dark energy, though I have to be honest, this also would be phantom dark energy, so it's not very easy to do this. But let's say you can do this, you get different change at all of these different redshifts, meaning that if you want now your dA of z to be correct, for example, you can do it in one BAO bin, but you cannot at the same time do it at CMB. So what you then have to do, you have to be, okay, so what do I do? Well, I simply say, okay, I have some more dark radiation here, then I go back, and then I go up, and then I go back, and then go up, and then go back, and you get some wave-like features, which is what a lot of these Gaussian process analyses of late time h of z data usually get when they try to do this. However, what I should mention for these is, of course, that you do have more freedom in this dark energy term, because it's basically like no one knows what it is. So you can do basically anything with it. And even a lot of phenomenological models are coming out on this. So early time solution, kind of different idea. The idea is that you change the sound horizon, and thus everything kind of falls in place. And I'm going to show you very nicely how it works. So you would change h naught, everything moves up. You change RS, and suddenly this factor here, it exactly cancels out, because you see the sound horizon is only RS times h naught. So if you do one and the other, it doesn't change the overall result anymore for all redshifts. So that's why you get kind of the same effect on all redshift, meaning that this is a very convenient avenue to do it without destroying a lot of these BAO and CMD measurements. There's some problems usually with this. So if you have dark radiation solutions, there's usually that you incur also some perturbations, which increase, for example, the silt damping of your CMB, and then you suddenly get into overdamped CMB tails, which then you somehow have to correct by adjusting the other cosmological parameters, and then your model is excluded again. Or you get into increasing an effective too much, you get into BBN. It's always something like this that kind of prevents these dark radiation solutions. Though I should mention that there has been recently a paper on stepped dark radiation, which kind of tries to have low and effective at early times, and then have a big and effective at late times. And this kind of seems to, or appears to, solve this tension, though I should be mentioning that I'm currently investigating this model, and maybe it might be killed in the future, who knows. So the other problem that these models usually have is motivation currently. So of course we are theorists, we can try to come up with a lot of interesting models, but you have to somehow have a theory for this model. This is also where a lot of these models are lacking. This WZ dark radiation model is also very nice because of its kind of simplistic model as from some SUSY basically. But there are some other models like inhomogeneous recombination and varying electron mass, which are kind of harder to motivate because they require you to play around with fundamental constants of the universe and so on and so forth, which is not always very easy. Okay, so if we look at the review, for example, on Eleonora, we see that there's a lot of different models compared along the different data sets. And that is, of course, sometimes a bit difficult because if we try to compare these two models, we see that one of them does not contain R19, the other one does contain R19. So it's basically kind of an unfair comparison. Because if I use this model and I add R19, I can almost assure you it's going to move to the right. And if I take this model and I don't use R19, it's going to move to the left. That's almost certain. So this different data thing we cannot do. So we need a fair comparison, which is where the Asian Olympics paper advertisement comes in. Our approach, of course, using the same data sets. So in this case, Planck 2018, BAO supernovae. And we, of course, tested also what happens with more or less data. Objective criteria. So here I want to spend a little bit of time. So you can either have the Gaussian tension that is very often used if you have two mean values and two sigma error bars. You can do this kind of very easy estimation of the tension. However, this does not work in a lot of these models that are early universe solutions, because many of these early universe solutions, they have very asymmetric posteriors. Why is this? Well, if you have some extensions of lambda CDM that has more than one parameter, then, for example, one is the amount of stuff that you add, and the other one is controlling how the stuff behaves. Then the parameter controlling how the stuff behaves is completely irrelevant if the amplitude is 0, right? So this means that if you go at the very small amplitude, it's almost irrelevant. So this means that there will be like a problem with the amount of parameter space that you have, basically. So a lot of the parameter space will be very close to lambda CM, where the amplitude is close to 0, and the stuff can behave basically like anything. And then only when you go to high amplitudes, there is the kind of critical region that you actually care about, like where the stuff can only behave in a certain way to fix the H0 tension. This means that usually you get this problem that you have most of your stuff is lambda CDM, and then you have where your parameter gets slightly high, but this is from just the volume of parameter space, it's slightly suppressed. And this is where it might be more natural to talk about like the minimal chi-square values, either with Cepheids, without Cepheids. Take the difference, and if you do your minimization well, you also get the tension value for this. And so if you fit now your data, for example, with Planck without Cepheids, you will get basically a Planck best fit. And then you fit the data to Planck with Cepheids. Yes, your data will have to somehow compromise, right? You want to have a good best fit or good fit to the Cepheids and to Planck at the same time. So you land usually somewhere in the middle, somewhere where you're a bit worse with Planck, and somewhere where you're also a bit worse with, or a bit bad with the Cepheids. So actually, where you land is where this thing is slightly larger than this one. And depending on how large it is, you can derive this kind of tension value. If you take this precise formula, you will get the same tension as the Gaussian tension in the Gaussian limit. And this can be derived very easily if you just plug in the multivariate Gaussian distributions. Then you take like You minimize them, you get what is the mean and the sigma out of it, basically, or the mean and the covariance matrix, and then you can derive this kind of Gaussian tension criterion. What is nice about the Cepheids is that if you choose the Cepheids to be this kind of prior, of course, the minimum chi-square of just taking Cepheids, of only taking Cepheids, is of course always going to be just 0. Because you can then take your MB value to be exactly what choose determines, and then you're in the middle of this prior. And then, of course, you don't have an offset of your chi-square anymore. So this is where I'm being a bit tricky by just writing the difference between two, but it simplifies the formula there. So this is just a side note. Okay. Now, why is this not enough? So you have a model which reduces these two criteria. It reduces the Gaussian tension, it reduces the QD tension. It's basically like your perfect model. So this I've drawn here. So I have lambda CDM and I have my model here. And now I'm done, right? I have a model which very well agrees with Cepheids. I'm basically like, I can publish my paper now. And this is what a lot of people do indirectly. But it's not very good thing to do. Because, okay, the red one has 4.4 sigma, the blue one has roughly 1 sigma. So you can vote now. Do you think the blue model is good or not? Best model, right? Except that there's a huge problem with this model. This model is actually disfavored by Planck data by delta chi-square of around 100. So what happened? So how can I find the best fit in a model which is disfavored by Planck data by such a huge delta chi-square? Like it means that it's not at all a good fit to the Planck data. This lambda CDM model is much better. Now I can tell you that the model that I've chosen is actually very simple. I simply adjusted the omega CDM, so the amount of physical CDM, so big omega CDM times h squared, to be 0.11, I think, which is not the Planck best fit. But it's the one where if you go along the degeneracy line of H0 and omega CDM in Planck, you will actually find a very good H0. So the fundamental problem is that I have basically ignored how well a model fits to my data. So if I am allowed to fix any parameter of my model, I can always get arbitrarily well to the H0 value of the Cepheids. So I can always reduce my tension arbitrarily well. Because if I don't care about how well I fix the model, I can just take the model of the Cepheids, fix my model there, and then just say, oh, the tension is gone. Because then I will have a model perfectly fitting the Cepheids, and there will not be a difference anymore. So what went fundamentally wrong is that we simply fixed some parameters of the model. And what does it mean for the model? Now, the model is not anymore a sub-model of the lambda CDM model, or something that includes the lambda CDM model. So that is the fundamental problem. If you have a model where lambda CDM is a subcase, and you try to fit it to the data, your chi-square will always be better than lambda CDM. Because otherwise, if you have some random chi-square here, some random chi-square here, your MCMC, it can always go to the best chi-square. It can always go where lambda CDM is, at least. What it can then do is it can try to explore some new directions where it can get better than lambda CDM, but it cannot be worse. So that is one fundamental truth here, that the chi-square of a model that has lambda CDM as some nested subcase will always be better or equal to lambda CDM. And thus, you don't have to worry about it. This is why very often you just see people quoting these two tensions and done. Because you don't have to worry about what I will talk about next if your lambda CDM model is a nested subcase. However, if it isn't, then you have a huge problem. And this actually turns out to be nowadays relevant because more and more people are proposing models and they are just fixing random parameters. So it happened to myself already twice that I investigated a model where somebody had fixed the parameter and then the model worked, but only because they fixed this parameter. And then if you release this parameter, the model had now a better chi-square than lambda CDM again, but it was total crap for the Hubble tension. So my advice is, if your model does not clearly include the subcase where you definitely return to the lambda CDM limit, you should always look at the chi-square minimal
of this model compared to the chi-square minimal of lambda CDM. Now you can simply do that, and you already kind of saved, or you can do a step further, as we did in this paper, and define some new threshold. In this case, it's the chi-square information criteria. It's a very simple idea. Just look at the chi-square of the model minus the chi-square of lambda CDM. That's basically already it. That's exactly what we talked about. If the model is a very, very good fit to Planck, then this will be much smaller than this. And your AIC will be very negative, will be like -5 or so. Then you would say, oh, that's a good model. However, you also get some penalty here, some additional positive term from the number of parameters. So if you have 10 million parameters, of course you can fit anything arbitrarily well, but this thing will penalize it in this case. So if you have 10 million additional parameters, you have to include, reduce your chi-square at least by minus 20 million, sorry, by minus 20 million in order for this to come out to 0. So then you suddenly raise the bar. If you have more parameters, it's more difficult. Now this is just one example of many such criteria that exist out there. So there's, for example, the Bayesian information criteria. There's a lot of new ones that have been proposed very recently. This factor 2 is basically all that the difference boils down to, because this is just a penalization based on, like, why is there factor 2? It's based on, in this case, on some information criterion condition. But you could imagine that if you have more data, then you would want to penalize it stronger. Or if you have less data, you would penalize less strongly. Then you would, for example, use the Bayesian information criteria. All of this is somehow to emulate, in a sense, this Occam's razor argument that you want to have a model with the least parameters. Now, you could also do it by looking at Bayesian evidences, but sometimes it's a bit difficult to estimate these Bayesian evidences, because for this you need to integrate over the whole parameter space. Okay, so of course we imposed additional criteria because we wanted to knock out these models which have delta chi-square of 100 compared to lambda CDM. So the model also has to fit the data back from lambda CDM. Now the last part is that we base our attention on the absolute magnitude of the supernova themselves instead of the Hubble parameter. This is because the Hubble tension is not actually about the Hubble parameter, as we touched upon in the last part, because this is plotted by ICCUB in 2021, and I think it demonstrates it very nicely. So here we see the true H0. That's the H0 basically that is in the model. So this is one specific model, and here you can just see what kind of H0 models the H0 values the model predicts. So this would be the output of your Boltzmann code or whatever cosmological inference. Now this is the H0 that the Schuh's collaboration with the analysis, so the whole analysis script in place, they're using the supernova and so on and so forth with the distance ladder, what they would get out as the H0 value. And you can see it's almost this vertical line that it should be, where just the value of H0 of the model is the value of H0 that the Schuh's analysis would get out, but it's not quite. And this is because this model here has been specifically chosen in order to demonstrate this tail here, where the model predicts a high value, H0 equal 74, but the Schuh's analysis, if you would perform it on this particular model, would give you an H0 value of 68. Now, why is this the case, that the Schuh's analysis can give you a different H0 value than the H0 value of the model? This is because the model is violating some assumptions of the Schuh's analysis, which is that there's no crazy change of the expansion history between basically supernova and today. So this kind of is a crazy model. However, it means that you have to be careful about these models. So it doesn't tell you that the whole Schuh's analysis is wrong or anything. It just tells you that you have to be somewhere careful. So they're doing, for example, a cosmographic expansion of the Hubble parameter, which would break down in this kind of crazy model, in some sense. Okay, what is the simple thing that you can do? Well, you can simply repeat kind of the analysis. So basically, these two steps are almost safe because there's not much that can go wrong here. You could, of course, imagine like a transition, a strong, sharp transition of some properties of these calibrators in some intermediate regime, or some cosmology which modifies the luminosity distance. down here, but actually the redshift that this is happening, this kind of calibration of the supernova, is relatively low. So usually the calibration of the supernova is relatively robust. However, the second step of the influence of the supernova, you could imagine there could something go very wrong. So these are almost like local objects, these satellites. But the way that we calibrate the supernovae on them and that we use the supernovae, that is very much dependent on, or could be dependent on your cosmology. So the distinction here is a tiny bit arbitrary, I have to openly say, because I don't want to make an advertisement, meaning that if you have a model which modifies even like redshift 0.000000001, you could break this step here. But let's assume that we have somewhere close to a reasonable model, then usually this will be the step that's broken. And thus, you just can take the MB value from shoes, but you do the last step yourself, basically, with the Pantheon supernovae data, and etc., etc. So that's why we put prior on MB instead of H0. We just look at what kind of prior of MB would correspond to the value of H0 that the shoes collaboration at first, using, for example, the Pantheon supernovae. And then we take that as a prior on our MB. So what are the results? So this is now for an arbitrary selection of models. First of all, let's start with late universe solutions, which we've seen have a very difficult time because the sound horizon is fixed. The angular size of the sound horizon is measured well. So you have to play around with angular diameter distance. What kind of models did we consider? And this is kind of where we have a bit of lack. So we only considered this PEDE model, which is phenomenologically emergent dark energy by Di Valentino et al. We considered an expansion of the dark energy equation of state in low redshift. And we considered two models in which dark matter is decaying into something. So this was I was talking about before. You can do some change of the W of Z. You can do some phenomenologically motivated change of the W of Z, or you can let dark matter somehow disappear. Now, letting dark matter disappear, you can see it doesn't do enough, basically, because usually you're left with some decay relics, which have some strong impact on other observables. And if you want these decay relics not to mess up everything else, you have to constrain your model in such a way that also doesn't impact the Hubble tension strongly. That is kind of the takeaway of this. So then you're left with dark energy. With dark energy, you can do a lot more. So for example, here the CPL expansion. If you just have Planck-BAO, then actually you can kind of ease this tension a bit. You see that you have now very broad error bars in the Planck-BAO phase itself. And if you then use the shoes prior, you actually get very close to shoes result as well, which kind of tells you that the chi-square of shoes in this case cannot be very bad. So what you would find also, if you look into the paper, you look at the table, you would find that this kind of has okay criteria. It's not super bad. However, as soon as you add supernovae, this model becomes highly disfavored because the supernovae actually constrain the way that you can deviate from the equation of state of -1 in a strong way. So then you kind of lose all the advantage of this model, basically. Okay. Similarly, phenomenologically emergent dark energy, there you see the mean value is already very close to shoes. Wow, great thing. Two things. One, it is not a nested submodel of lambda-CDM, so it would technically be excluded if we choose this kind of criterion that it has to fit at least as well as lambda-CDM. So there's this problem with the nestedness. Second problem, if you add supernovae, it performs a lot less good because it has some non-trivial change of the equation of state, exactly where the supernovae are sitting and are able to constrain this. And so you kind of get a lot farther from where you want to be. Okay, so these supernovae kind of make a strike. So what is MPD? MPD is basically the same, except that you add a parameter to make it a nested subcase of lambda-CDM. So you have one parameter that goes from 0 for PED to 1 for lambda-CDM. And suddenly you can see the model does nothing anymore. And so this is, once again, a careful tale about including your lambda-CDM model as a nested subcase. Let's say late universe solutions don't work, let's try to use early universe solutions. So we have a couple of models here of dark radiation. So basically, usual and effective model. This is just where you add some dark radiation, free streaming. You do nothing more with it. It performs okay, but not super well. And then there were a lot of proposals that tried to kind of advance this model a slight bit in order to get better at solving the Hubble tension. And what is the biggest problem of this ineffective model here? Problem is actually the additional silk damping that you introduce. So by including some dark radiation, what actually happens is you have more free streaming stuff around and a different expansion rate of the universe. This actually leads to the damping case of the CMB getting enhanced. So usually the difference between a model with a high N effective and a low N effective is this additional damping of the high L multipoles of the damping tail of the CMB. So there's different ways that you try to mitigate this. So the biggest problem is that these things are free streaming. So they have like a lot of impact on the free streaming radiation as well. If you already consider them to be self-enacting, such as you suppress the free stream by letting them self-enact, which means that they form a fluid instead, they don't couple as strongly anymore to the usual radiation, and the CMB damping plates are a bit less. So you basically prevent the free streaming of these dark radiation species, and thus you have like a little bit more of a leeway. You can mix the two models, get basically a very similar result. Or you can now ask ourselves, what else can I do with the dark radiation instead of just making it self-enacting? You can let it interact with dark matter, that's shown here, or you can interact it with neutrinos, in this case self-enacting neutrinos. This has been shown in the past to be a reasonable solution, but actually with the Planck 2018 polarization data, it does not seem to be the best solution anymore. Okay. And then we have the marginal model, which is kind of an in-between between the early universe models and the dark radiation models. It's basically a model of dark radiation, but it also has some non-trivial evolution of the expansion rate, h of z, and it does slightly better. But for the details of the marginal, you can read the paper on the marginal. It's a bit too much to explain now. However, let's get to the last part. So the early universe models. So these are the ones which are actually changing the sound horizon by just including some other mechanism other than dark radiation. So all of these are kind of hampered by the Planck polarization because they kind of change the damping tail. These not necessarily, depends on the model. So for example, you can see that we have here the varying electron mass model, and it performs reasonably well here and here. And if you include a curvature, you actually give it more freedom. So the varying electron mass cannot, it changes recombination, but this also changes, for example, the angular diameter distance to recombination. And if you give it some curvature, you can kind of readjust it, rebalance it. And this will actually lead you to have a model which very nicely can solve the Cepheids, but is very hard to motivate. We have two other models here. We have the primordial magnetic fields, which don't perform stellarly, but they are perhaps one of the most well-motivated ones because you just need like approximately nano-Gauss primordial magnetic fields, which are kind of nice because they could also correspond to the current extragalactic magnetic field. So there's some people who really like this model. But this model is more and more getting disfavored by letting some parameters which were previously fixed now free, and it's looking less and less likely. Then we have the early dark energy model, which is still strong, but it's still fine-tuned. So it's still very much so that you have to kind of adjust the time at which dark energy disappears exactly to be before recombination. And there's not much that you can do about this curve. There's not yet something where you say, okay, matter radiation equality triggers early dark energy to disappear or something. This is not yet in any model. There's also one model here which is missing, which was only released just after we submitted the second version of our paper, which is the Weiss-Zumino dark radiation model, which is basically the same as the self-enacting dark radiation, except with a little twist. The twist is that you have different amount of dark radiation in the very, very early universe and in the early universe. So this means above redshift of around 5 times 10 to the 4 and after redshift of 5 times 10 to the 4. You have different amounts of this biseminidar radiation, which means that you also have different amounts of suppression or these kind of different amount of diffusion damping in these models. And this actually allows you to play around with it in such a way that you actually do recover a nice fit for the Planck results. Speaking of the results, so what we saw before were all Gaussian results. Now I want to show you slightly different results. First, the delta chi-squares, which are basically what we talked about before. It's the QDMAP criterion. It's this criterion that generalizes the Gaussian one. And you can see that most of these models kind of have very similar thresholds as on the previous slide. So the models that were good on this slide are also good on this slide. The biggest impact is actually for EDE and NED models, which before they looked okay, now they look stellar. Like now they are like, oh wow, what a great model. This is because this Gaussian error bar here doesn't quite reflect the non-Gaussianity of this posterior. And this is why suddenly it looks much better than on the other plot. But it's basically only these models here that get majorly affected. There's also early modified gravity here, by the way. That's just snuck in. Early modified gravity is basically the same idea as the early dark energy, except that you, instead of having some dark energy fluid at early times, you have some modification of gravity only at early times. From the other models here, we see that they are still similarly performing. The best ones that we have here is the PEDE, early dark energy and early modified gravity, and this varying electron mass. Summarize, now we just have metals, because this was about H100 paper, so we have to give some metals. So we just have 3 tests: Gaussian tension, AIC, and we just rate them how many of these tests they pass, 3 to 1. Okay. So silver medals for primordial magnetic fields have the neckling variation. Bronze medal. Silver medal for early dark energy, modified gravity in the early universe, and the Majoron model, and the gold medal for the varying electron mass, or in addition with curvature. And that's basically the summary of the result. I should note here that these 2 medals here are a lot closer than these 3. Because the Gaussian description of the posterior is not a good description for many of these models. So requiring the Gaussian tension to be passed as well is kind of not a good thing for all 3 of these models. So in some sense, early dark energy and early modified gravity could also get a gold medal.
But you needed 3 criteria.
Yeah, exactly. But you needed 3 criteria for 3 medals. So what else can you do? Exactly. Okay, and that's already it. Thanks for listening.